All right, ladies and gentlemen, here we go. What we're going to be discussing today is how we can write a polynomial in factored form using the factor theorem. So what we're talking about here is that, first of all, again, just a quick reminder what the factor theorem is basically saying that if you substitute the solution to a factor, like say for instance we have a factor that says x plus 3. The solution to that factor would be x is equal to negative 3. If we take that solution and we substitute it into the problem and evaluate it, and we get a 0, that tells you that it's a factor. You can also identify a factor by doing division, either long division or synthetic division. If the remainder of the division problem is a 0, that also tells you this is a factor. And that's pretty much what we have been kind of leading up to over the course of the instruction with synthetic division, long division, the remainder theorem, all that stuff has kind of been leading up to this idea, because what we're going to be using it for is at some point is to graph a function based off of its end behavior and what its zeros are, what its solutions are. So here is kind of the process of what we're going to be doing when we are trying to factor a polynomial. Now, we've been factoring quadratics for a good amount. We've done a few factoring of third degree polynomials where we can factor by grouping. But this process is going to be leading us into how we can factor any polynomial regardless of the degree. Now, we're not going to get ridiculously crazy with it. We're not going to give you like a 10th degree polynomial and ask you to factor it. But we would the process that we're going to use will work for really any polynomial that is third degree or higher. So we'll start by using synthetic division to make sure the factor that we have is a factor of the polynomial. Once we've established that, we have what we would refer to as a simplified polynomial. That simplified polynomial is usually something that can be factored further, either through more synthetic division or simply by factoring it if it is small enough or has opportunity for us. So like, for instance, if we have something that is some third degree polynomial, usually we can factor that one either by grouping or using a second synthetic division process. So that's what we're going to be taking a look at. So here we have a third degree polynomial. Now, if we tried factoring this particular polynomial by grouping, it really would not, it really wouldn't work out by factoring by grouping. In the first two terms, the x cubed and the x squared term, we could factor out an x squared. But in the second two terms, there's not really a common factor besides 2 that would be able to factor it out and give us something that we could continue factoring with. So factoring by grouping, unfortunately, is not going to work out very well for this one. So that leaves us with going with synthetic division. Now, here we have a solution, x is equal to 2. The factor that would have produced the solution would have been an x minus 2. That would have been the factor. Now, we're going to take the 2 and do our synthetic division process with it. So again, as with any division process with polynomials, long division or synthetic division, we want to make sure before we do anything, as we set up the problem, are there any exponents missing that we would have to put in a 0 for a placeholder. So it's a third degree polynomial. Largest exponent is 3. That's why we call it third degree. So 3, 2, and the exponent 1 is present. So all of the exponents are accounted for, so we don't have to put any 0 placeholders. The leading coefficient is 1, next coefficient negative 3, negative 10, and the constant is a positive 24. We're going to run through the synthetic process here, synthetic division, bring down the 1, multiply, it gives me a 2, add those together, which gives me a negative 1, multiply those together, negative 2, add for a negative 12, and multiply for a negative 24. And this right here is a good sign, because when we combine those, it gives us a remainder of 0. Basically what that tells you is that the x minus 2 factor is going to be a factor of the third degree polynomial. Now, this right here, the quotient that we would get if we wrote it out is a x squared minus x. Oop, I'll touch the board in too many places here. Let me clean that up just a bit. X squared minus x minus 12. This is what I would refer to as a simplified polynomial, because that would be the quotient of the third degree polynomial after we factored out the x minus 2. So what we would be left with if we were writing this function out in factored form, well, the x equals 2, again, the factor that would have presented that or produced that would have been a factor of x minus 2. And we also have the x squared minus x minus 12 simplified polynomial. If we were to multiply the x minus 2 factor into the quadratic one, we would wind back up where we started with. And that's, not exactly what we want to do right now. We're trying to put it in factored form. Now, the simplified polynomial, generally speaking, the types of problems that we're going to be working with, these are factorable. And the reason why they're factorable is because, generally speaking, the problems are chosen in such a way that they're almost always going to give you something that's factorable that will give you a real solution. Now, not always are they going to be real solutions. It is possible that we could have some imaginary solutions. But in the meantime, let's take a look at what we have. Right now we have a quadratic x squared minus x minus 12. Well, that quadratic can be broken up into its factors of an x minus 4 and an x plus a 3. Now again, going back to things I've repeated several times in class, first of all, it is a third degree polynomial. That means there has to be 3 solutions. Those solutions come from each of these 3 factors. So here we have x minus 2 as a factor, x minus 4 as a factor, and x plus 3 as a factor. So if I asked you what would be the solutions of this polynomial, you could say that x would equal to 2, x would equal to 4, and x would equal to a negative 3. But that's not where we're headed with this just yet. All we're doing right now is simply taking the standard polynomial and putting it in factored form, which is what we have here. The next example that we see is a fourth degree polynomial. Now again, there should be 4 solutions, 4 factors, however you want to think of it. And we're provided with the solution of x is equal to a negative 1. So the factor that would have produced this one would be x plus 1, because if I set that equal to 0 and solve for x, that's where the negative 1 comes from. So we're going to do the synthetic division with the negative 1. Excuse me. Now, looking at the fourth degree polynomial, all of the exponents are present, so I don't need any 0 placeholders. So the leading coefficient is 1, the next one is 2, negative 3, negative 8, and negative 4 for my constant. So go through the synthetic division process, and ideally at the end we should have a remainder of 0. So bring down the 1, multiply negative 1, and add those together, which is a 1. Multiply those, which will give me a negative 1. Add those, which will give me a negative 4. Multiply those, positive 5. Oops, sorry, getting ahead of myself. Negative 1 times negative 4 is a positive 4, which when I add those will give me a negative 4. And multiply again negative times negative to give me a positive 4, which we can see that's going to make me happy because it gives me a remainder of 0. So that tells you that the factor x plus 1 is a factor of the fourth degree polynomial, or you could look at it as x is equal to negative 1 is one of the 4 solutions of the fourth degree polynomial. So let's write out what is the simplified polynomial that we have. So we started off with a fourth degree polynomial, divided an x out of it. So that means this is a third degree polynomial for the quotient here. So this would be 1x cubed plus x squared minus 4x minus 4. So this is going to be our simplified polynomial. that we will use to see, well, how are we going to try and factor this further? Now, we could use synthetic division here if we knew more of the factors. Well, unfortunately, more of the factors aren't given to us, and I haven't shown you how to figure out what a factor would be when it's not given to you, so we're not going to try that yet. Now, the nice thing is that, again, even though this is a simplified polynomial that is a cubic third degree polynomial, this also is factorable. It's factorable by grouping. We can factor out an x squared out of the first two terms and a -4 out of the second two terms. So let's rewrite the factor, or let's rewrite the polynomial for what we have so far. We've established that the first factor was given to us, well, not directly, but it was given to us to be x plus 1. And at this time, we have the simplified polynomial to be x cubed plus x squared minus 4x minus 4. Now at this point, again, if we were trying to write it in standard form from what we've done in previous lessons, we would multiply the x plus 1 into the polynomial on the right and wind up with back where we started, but that's not what we want to try and do. So we want to see, can we factor that third degree polynomial? And we can. It can be factored by grouping. So at this point here, and I'm going to use a bracket just to kind of separate the parentheses so they don't all kind of look together. I can factor out an x squared from the first two terms, and I'll be left with x plus 1. And I can factor out a -4 from the second two terms, and I'll be left with a factor of, again, x plus 1. So inside of the brackets, we can factor out the x plus 1 factor from each of the two terms that we have. So now I'll have x plus 1 times x squared minus 4. Now at this point, some of us are going to think, well, we're probably done. But at this point right now, we really only have 3 factors. And the fact that this is a fourth degree polynomial says there has to be 4. Well, that x squared minus 4 factor is the difference of 2 squares. This can still be factored. So let's go ahead and factor it. Here we still have x plus 1 times x plus 1. And the x squared minus 4 can be factored to be x plus 2 and x minus 2. So here you can see now we do have the 4 factors, which would provide 4 solutions. Now the only other thing that we want to do here, this part right here, I probably would not consider to be wrong, but I want you guys to understand as a student that because we have a factor that repeats itself, x plus 1, that we can write that factor as x plus 1 squared. And that's almost always how you would see it. Like if it was a multiple choice answer on a test, you would not see it as x plus 1 times x plus 1. You'd see it as x plus 1 squared. And so we have the other 2 factors, x plus 2 times x minus 2. So the fact that we have one factor that is squared tells us, well, that is 2 factors. It just happens to be the same number that will repeat itself. And we'll talk about that a little bit more about that a little later on, but relating that back to quadratics that we've been talking about, that essentially tells you that at the solution, where x is equal to -1, that the polynomial will simply touch the x-axis there and then kind of bounce off of it, kind of like the way a quadratic would when it touched the x-axis at only one place. And that would be the final factored form of the fourth degree polynomial that you see there. And unfortunately, we don't have a whole lot more examples to give you guys right now, but if you have any questions, please make sure you have them written down, bring them to me in class, and we'll see you soon.